Coming up on SciTech Now, on alert for earthquakes.
With our network, we feel like we can detect and locate any seismic event that's a magnitude 2 or larger.
Finding the speed of light with peeps.
The speed of light is one of those numbers that people have chased for centuries. Today, I can find the speed of light in my kitchen.
How forests use water.
The strength in what we do here is that we've got continuous measurements, and what we've seen over time is our dry years are getting drier.
Funding for this program is made possible by the Corporation for Public Broadcasting, Sue and Edgar Wackenheim III, and contributions to this station.
I'm Mike Zeman. Thanks for watching SciTech Now. You don't typically associate Pennsylvania with earthquakes, but a network of 30 motion sensors are continuously monitoring the state for seismic activity. We wanted to find out why. Here's the story.
We remember the big ones, even if we weren't around for them. 1906, San Francisco. 1964, Prince William Sound, Alaska. 1994, Northridge, California. In Pennsylvania, big earthquakes are rare. The biggest, 5.2 in 1998. But PA has its fair share of little ones. Since the beginning of 2015, there have been 12 earthquakes in the Commonwealth, none larger than magnitude 2.6. Most are so minor, you wouldn't even notice them. But the Pennsylvania State Seismic Network doesn't miss much.
With our network, we feel like we can detect and locate any seismic event that's a magnitude 2 or larger.
Andrew Nyblade is a professor of geosciences at Penn State. He led the team that installed the network.
There's actually 3 separate sensors in each one of these canisters.
It started in 2006 as a way for the Pennsylvania Department of Conservation and Natural Resources to get a better read on earthquake activity.
There is natural seismicity in Pennsylvania. There's 2 areas where earthquakes have occurred historically. One is in the southeastern part of the state, particularly in the Lancaster-Reading area, and then also up around Erie, along the border between Ohio and Pennsylvania in the northwestern part of the state.
In 2015, the network expanded, and so did its focus.
The expansion in 2015 came about because of the increased activities in oil and gas exploration, fracking in particular, the need or the interest in expanding the number of wastewater disposal wells within the Commonwealth.
The DCNR wanted a way to track what is known as induced seismicity, or earthquakes caused by human activity.
Oklahoma in particular, Texas, Kansas, Ohio now, there have been a fair number of seismic events that have been induced by oil and gas activity, whether it's fracking or wastewater injection. The concern here is that as oil and gas activity further develops in Pennsylvania, in particular as more disposal wells are permitted and come online, that there could be a ramp up in induced seismicity within Pennsylvania.
According to the EPA, there has only been 1 fracking-related earthquake in Pennsylvania, but Nyblade believes monitoring can help improve safety.
If induced seismicity is happening, at what level is it acceptable, and what level do they need to work with the operators to modify their operations or shut down their operations?
The monitoring begins at stations like this one at Penn State, one of 30 scattered across the Commonwealth.
The concrete pier here is part of a seismic station that was built when this building was built in the early 1960s. It's a concrete pier that goes down to bedrock and is decoupled from the building.
The sensors at each station record motion in 3 different directions: vertical, north-south, and east-west.
I'll do a tap on top of the pier, and that should record primarily vertical motion from the sensor, and then we can tap the side of the pier in each direction, and if I tap it correctly, then we should be able to see the larger amplitude corresponding to the direction of the tap. Again, here's the pulses from hitting it to the north and south. You can see that the north and south is a little bit bigger than the east and west component.
This 3-dimensional monitoring comes in handy when it comes time to separate earthquakes from everything else. The most common event, mine blasts.
Blasting events occur, pretty much Monday through Friday during working hours, daylight hours. They're not allowed to blast in the nighttime event. So if there is an event in the middle of the night, for example, we can immediately roll that out as a blasting event. In the daytime, if there's an event, we have to look at more of the frequency content of the waveform, the actual arrivals themselves. Real earthquakes and induced earthquakes have more impulsive arrivals, so the peaks come in sharper. The blasts are typically more emergent, so they come in a little bit slower to reach their peak amplitude.
Each event is recorded in real time and posted online. And even though magnitudes being measured aren't earth-shattering, by keeping a close eye on the little ones, scientists hope to better understand the natural world and how humans are making an impact.
What do you get when you combine a microwave and a pan full of those pastel-colored marshmallows known as peeps? NPR's science reporter Adam Cole demonstrates how the squishy mess can actually help you calculate the speed of light.
It's the week after Easter, and that means homes all across America are overflowing with stale peeps. Now, you could either eat those peeps, or you could use them to find the speed of light.
Finding speed of light with peeps.
The speed of light is one of those numbers that people have chased for centuries. Galileo wanted to know how fast light moves.
Buonasera.
So he proposed an experiment.
Facciamolo.
He would uncover a lantern, and when the light reached his assistant, the assistant would quickly uncover his own lantern. Using a water clock, Galileo would keep track of the time between uncovering his light and seeing his assistant's light. Up close, there was no noticeable delay except for the split second it took his assistant to react. Then they started moving away from each other. Galileo figured the delay would get longer and longer because the light would need more time to travel the greater distance. But even when they were a mile apart, there wasn't a noticeable pause.
Che rabbia.
He couldn't have guessed that light had made that trip in 100,000th of a second. Centuries later, in 1849, a French scientist, whose name I can't pronounce,
Armand Hippolyte Louis Fizeau,
came up with an even better way to measure the speed of light, which was pretty impressive considering that people weren't even using light bulbs yet. He took a toothed wheel and spun it faster and faster. He shot a beam of light between the teeth and reflected that beam of light off a mere 5 miles away. By the time the light got back, a tiny fraction of a second later, the teeth had moved over just enough to block the light. No light made it back through. But if he made the wheel spin a little faster, the teeth would move over one whole position and the light could get through. So when
Fizeau
saw the light, he knew the wheel was spinning so fast that a single tooth was moving over one place in the time it took light to travel 10 miles. With some quick math,
Armand Hippolyte Louis Fizeau
determined that the speed of light was 700 million miles per hour, which we now know was only 5% off the actual value. Today, I can find the speed of light in my kitchen, and that brings us back to peeps.
Finding speed of light with peeps.
And a microwave.
And a microwave.
And just a little bit of physics.
And physics. Just a little bit.
Microwaves travel at the speed of light. And like all waves, their speed is determined by how fast they go up and down, that's the frequency, and their wavelength. The frequency is written on the side of my microwave right here, 2,450 megahertz. So we've got the frequency. Now to calculate the speed, we just need to know the wavelength. And we can find the wavelength by microwaving peeps. I'll set it on low so the peeps don't just explode. And let it run for a minute or two. Inside, microwaves are bouncing around. In some spots, there isn't much energy at all, and the peeps in those areas stay cold. In other spots, there's lots of energy, and the peeps get really hot. Those hot spots are half a wavelength apart. So in theory, if I measure the distance between melted peeps, I can find the wavelength. And sure enough, some of the peeps are really gooey, while others haven't melted at all. Poking around, I found a rough location for a handful of hot spots, and I measured the distance between them. Those average out to 2.43 inches, so that's half a wavelength. Multiply by 2 and we get a wavelength of 4.86 inches. So now to find the speed of the microwaves, which remember is the speed of light, I just have to do the math. Frequency times wavelength, 2,450 megahertz times 4.86 inches gives us about 12 billion inches per second, or 676 million miles per hour. And that's pretty close to the actual speed of light.
We just found the speed of light with peeps.
Joining me now is Adam Cole, the creator and host of NPR's science YouTube channel, Skunk Bear. How many different ways are there of measuring the speed of light?
Well, there's been a lot throughout history. As soon as people figured out that light was moving, which was for a long time mysterious, they wanted to know if it traveled instantaneously from one point to another or if it actually had a speed. And so there's been a lot of contraptions created since basically the 1600s to try and experimentally determine this. People use rotating mirrors and toothed wheels like we saw in the video. People looked at the ticking clock that is the moons of Jupiter eclipsing to try and have a measurement of time and light passing between that planet and ours. So there's been a lot of different methods, and some that were more theoretical, using the constants of physics to try and figure out the speed of light.
So this peeps method...
it's probably the most serious of them all, and the most precise.
That's right. We're talking about wavelength and frequency. What's the difference?
The difference between wavelength and frequency? Well, wavelength is the distance between, if you think about a wave in the ocean, the distance between two troughs when a wave goes up and down, the distance from this low and this low is the wavelength. And the frequency is how fast that wave goes up and down. So you can think of it as the speed of a person walking is determined by the length of their step and the number of steps they take per second. And you multiply those together, you get the speed of them walking, multiply wavelength and frequency, you get the speed of a wave.
Okay, so this is an experiment that you would recommend that people try at home.
I hope that they do.
Were the marshmallows delicious after? I mean,
you know, I think I didn't have a lot of love for Peeps before this experiment, and after I definitely don't.
All right, Adam Cole from the YouTube channel for NPR, Skunk Bear. Thanks so much.
Thank you.
As young children, we learn a hard truth. In the end, all animals die. Or do they? Next up, we have the story of an ongoing science experiment and a freshwater animal that just may have found the fountain of youth.
One day, 250 years ago, a young teacher named Abraham Tremblay was walking through a field, and he came to a pond, looked in, and there in the water he saw this thing. It was very little, with wavy tentacles on top and a tube-like body. And just to see what would happen, he cut it in half. Much to his surprise, instead of dying on the spot, the animal grew back into 2 full-sized adults. So he did it again. The same thing happened. And again. This animal just wouldn't die. The Hydra, that's what it's called, has extraordinary powers of regeneration, almost as if it's built not to die ever, which is ridiculous because everything dies, we assume. In science, however, you don't assume, you check. So, in the 1990s, a curious young scientist, Daniel Martinez, having heard that hydras go on and on and on, decided to do an experiment. He gathered a bunch of hydra from a pond in Long Island, New York, put them in some tanks where he could keep an eye on them, and he thought, all right, I'm going to wait until I see them die naturally. And hydra do die. You take them out of water, they'll shrivel up. But in a natural environment, nobody knows. So Daniel waited. First his hydras had babies. Then a week passed. Then months passed. Meanwhile, Daniel's school year ended. He got a job out west in California. Rather than miss the death of his hydras, he put them in a cooler, traveled cross-country with his brother, and every day, wherever he was, he fed them, washed them, and he waited. A year passed. Then 2 years. 3 years. Still no deaths. 4 years out, Daniel published a science paper that said hydras apparently never die. Well, what he really said was, mortality patterns suggest lack of senescence in Hydra. Now, you'd think 4 years is kind of a short term for a claim like this. I mean, a lot of us are past our 4th birthdays and we still expect to die. But here's the thing. There's a well-known pattern in nature. The sooner you have babies, the sooner you die. If you're a tiny fly, you have your babies quickly after a couple of weeks, and you die here after a couple of months. If you're a huge elephant, you wait 13 years to have your babies, you live for another 40 or 50 years, and then you die right around here. And this is true across the animal kingdom, except when it comes to Hydra. Remember, Hydra have their babies after a couple of days, so they should die after, say, a month. But Dan's Hydra had lived for 4 years when he published his paper, and they are still going strong today. They've now lived for more than 8 years. That is 100 times their expected lifespan. That's like an elephant living for 5,000 years. It's like everybody else got the memo that in the end you die, but not the Hydra. So what's going on? Daniel says, here's my theory. Most animals, humans and hydras both, begin with a cell, a single cell, and they multiply. In humans, our cells multiply a lot, then specialize, age, break down, and eventually they wear out, and so we die. In a hydra, the cells, don't specialize much. Most hydra cells are embryonic cells, and embryonic cells, like embryos, they're simple and great at staying young. So you can watch them here, moving up the tentacles, moving down to the foot, and before they have a chance to get much older, they flake off to be replaced, as you see here, by newer cells. Over 4 years, the Hydra replaces all its cells, its entire body, over 60 times. Every cell in the body is completely new every 20 days. It even looks like a fountain of youth. So, for all intents and purposes, Daniel says, these animals are, and I want to use his word, immortal.
Joining me now is Adam Cole, the creator and host of NPR Science YouTube channel Skunk Bear. So how is it possible that these Hydra can keep doing this?
Well, it's all about simplicity for them. They don't have to create a lot of the specific organs or body systems that we do, and that means their cells can be very simple and just constantly replenished.
Where are they usually found?
They're usually found, well, there's all different subspecies or species of Hydra, and they're found just in freshwater ecosystems all over the world.
And has there been any controversy over the findings that Martinez had?
I think there's a lot of people who have called him and said, how can we make this into a facial cream or, these rejuvenating treatments? And I don't think he has much interest in that area.
And does Hydra have a natural predator or no?
I'm sure there's things that eat it. It's just one of those little squishy things that runs around. I'm sure there's, whatever's up the food chain, one rung is definitely eating them.
Are they unique in this, or are there any other?
There are some others. There's little planarian worms, these tiny worms that people believe have a similar ability. There's a jellyfish, tiny little jellyfish that people think also never dies. The thing they have in common is they're all very simple and all very small.
This makes me think of the agents of S.H.I.E.L.D., the Marvel, like always fighting Hydra,
Exactly.
cut off
Yeah,
one
right.
head, another one springs up.
Yep, and that's sort of, the legend of the Hydra is what gave name to that fictional organization and this animal.
All right, Adam Cole from NPR's Skunk Bear, thanks so much for joining us.
Thank you.
Learn more about the biologically immortal Hydra on our website, scitechnow.org.
An ongoing project in North Carolina is collecting data that could help scientists figure out how the natural water cycle changes with a changing climate. Take a look.
The rain that falls outside your window today is the same rain that watered the grounds and filled the streams and rivers millions of years ago during Earth's earliest days. That's right, the rain that was still is.
So we're interested into quantifying that, seeing how much it changes depending on the environmental conditions.
That's because rain, actually water, is vitally important to every living thing on the planet. And water is constantly cycling from earth to sky and back again.
So water in streams is important, obviously, right, for not only the fish and the critters that live in the stream, but also our water supplies.
It's called the hydrologic cycle. Let's follow this drop to see what happens. When the little water droplet becomes heavy enough, it falls from the clouds as snow or rain. Some of the water washes over the ground and flows into streams and rivers, and eventually into lakes and even the ocean. It evaporates back into the atmosphere, turning back into a cloud. Water droplets can also fall to earth and soak into the ground, and then be taken up by trees and plants. It's later released into the atmosphere through transpiration. But we're only now beginning to understand the specifics of the hydrologic cycle, thanks in part to the Coweta Hydrologic Laboratory in western North Carolina. The U.S. Forest Service bought the 5,600-acre forest and set it aside as an experimental forest back in 1934. The primary focus is on rainfall, stream flow, and how the forest uses water. One of the main research tools is a weir.
Again, it's called a weir, and this is one of the most precise ways you can use to measure how much water is coming down a stream.
A weir resembles a dam, but it's more than that. It's a stream gauging station built across a watershed. 32 weirs are built on various watersheds throughout the Coweta Basin.
So this wall extends all the way down to bedrock and extends all the way into the hill slope on one side of the stream. You can see it crosses the road and goes into this other hill slope. And so the idea is that you're taking all the water uphill of this weir, whatever's coming down the stream and whatever is moving in the shallow groundwater, and you're forcing that water to come over this, what we call a blade, this opening of the weir. So you're quantifying every bit of water leaving this watershed. You see the pond upstream of the wall. That pond is connected through pipes to a well inside of our gauge house. And so the height of the water inside this well is exactly the same as the height of the water in this pond. So in this well we have a float sitting on top of that water that's going up and down with the level of the water. And we record that with a time chart in the gauge house. And knowing the height of that water and the geometry of this weir, there's been experiments done to calculate flow as a function of the height of that water. So it's an equation, statistical equation that's calculating flow as a function of the height of the water.
Measuring stream flow gives a more accurate view of the water flowing through a watershed because rainfall varies over an area. And the weir system allows the watershed to be measured day and night through storm and sunshine.
But here we're measuring the height of this water to within 1 millimeter of its actual value.
Readings have been taken every 5 minutes since 1934. That's roughly 200 million bits of data. And that consistency is important.
The strength in what we do here is that we've got continuous measurements from one place over time with the same method. It's very consistent, very robust, and what we've seen over time is not that our mean is shifting up or down, so it's not getting uniformly wetter or uniformly drier, but our dry years are getting drier and our wet years are getting wetter.
The long trend of data shows the Coweta Basin still receives about the same amount of rain each year it's been getting for the past 80 years. But it also reveals that the dry years are getting drier, which means periods of drought are becoming more common and more severe. It also shows that wet periods are getting wetter, what many people call a torrential downpour with flooding. All of that will affect what plants, trees, and eventually animals live in the forest.
So we expect in the future, as our climate becomes more variable and we have more drier and more prolonged droughts, that we will see some species suffer as a result of that. So our species composition is going to be continuously changing.
To understand what those changes mean for the forest, dozens of experiments are studying sap flow in individual trees, soil moisture, and how the mineral content in the soil is changing. This instrument-laden tower measures just how much carbon the forest is taking in and releasing.
The leaves during the daytime are doing photosynthesis, so carbon dioxide enters the leaf, it gets transformed into a carbohydrate, into sugar. But at the same time, those leaves need to metabolize. They're like all of our cells. They basically have a certain cost of doing business. So they're breaking down a certain amount of carbon, releasing that back as carbon dioxide.
It takes a long time for these changes to manifest. It takes, especially given the variability we have in rainfall, you have to have a lot of data to be able to tease out a trend. Forests move slowly. It takes a long time for a forest to change, and so you can't do this in 10, 20 years. You have to have a long-term record to do it.
You can watch full episodes of SciTech Now on demand and online at wpsu.org/digital. I'm Mike Zeman. Thanks for watching.
Funding for this program is made possible by the Corporation for Public Broadcasting, Sue and Edgar Wachenheim III, and contributions to this station.